to join into the webinar today, and then we'll go ahead and get started. But for those of you in the Northern Hemisphere, hope you're enjoying your summer. And it's amazing how rapidly it's passing by. I can't believe we're already in the end of July. It's just blowing my mind. But anyway, we thank you for taking some time with us today for a really excellent presentation. I think you'll learn a lot and enjoy the presentation. So just give us another moment or two and we'll get started. While we're waiting, I just want to mention, and I'm sure I'll mention it 2 or 3 times, but we opened up registration for the IWCS 2025 Cable and Connectivity Industry Forum today, and so you may have gotten an email for that. So take advantage of the summer special pricing, and we hope to see you in Pittsburgh. So, okay. Well, why don't we go ahead and get started? And again, good morning, good afternoon, good evening. And I know some of you are registered from late into the evening. So hopefully you have a glass of wine. And we, again, thank you for being with us. Today, we have an excellent webinar. And my name, by the way, is Dave Cadu. I'm the CEO and Director of IWCS, and I'll be your moderator today. Just a few housekeeping items. As an attendee, you're part of a larger audience. So with that, during the presentation, all participants will be in listen-only mode. And again, the event is being recorded for rebroadcast. You'll be able to watch again or share it with your colleagues from our IWCS.org website or on our YouTube channel. We encourage you to ask questions as you are watching the presentation. If a question comes up or if you wish clarification, submit a written question in the chat. And if the chat panel should be on when you open it, on the right of your screen. And after typing your question at the space at the bottom, hit the send button. And your questions will be addressed, time permitting, at the end of the presentation. Today, we welcome Rick Tominelli. He's a consultant from Fiber Optic Center in Rhode Island, USA. And Rick will be presenting his paper today on an overview of rare earth doped fibers, applications and fabrication. Really interesting and neat technology. Rick Tominelli began his work at the Fiber Optic Center in 2020 as a rare earth doped optical fiber expert, a process development and manufacturing consultant as well. Rick retired from his position of Director of Engineering at the Coherent Fiber site in Salem, New Hampshire, a good New England boy, and has been working in the field of rare earth doped optical fibers for over 40 years. Prior to this position, he managed the specialty fiber group at JDS Uniphase, specializing in double-clad fibers for fiber lasers and erbium doped fiber. Rick also held positions in the optical group at Draper Laboratories and was a member of the Polaroid fiber optic team under the direction of Dr. Elias Schnitzer, which did much of the seminal work in rare earth doped fibers, fiber lasers and amplifiers. So really good collaboration there. He is a co-inventor of double-clad fiber laser pumping and has been granted 22 patents and 20 publications in fiber, lasers, and amplifiers. So Rick, we greatly thank you for being with us today, and take it away.
Okay, thank you, Dave. It's a pleasure to be here. Hello, everybody. Welcome to this presentation on rare earth dope fibers. Just a little overview again. This is an overview of what Dave just basically said about my past career activities. But let's get right into the presentation. So this is an overview. It's pretty, I would say, high level. It's not going to get into a lot of the details. It's going to just talk about the basics of what this whole technology is about. So let's first have a look at the rare earth, the periodic table here, and what are exactly the rare earths? Well, the rare earths compounds are these, or elements, are this series here that I'm pointing to, which is the lanthanide series. And the thing that's interesting about this series is that this is the first set of elements that we start filling what they call the F electron orbitals. So in this thing, I'm sure you probably know that this represents the S block orbitals, D orbitals, P orbitals, and this is the F orbitals. Now there's 7 different F orbitals, and so there's like 14 different energy levels that we can have here for all these different rare earths. So let's have just a quick review of it. First of all, I say it's a misnomer. They're not that rare. They're less rare than gold and platinum. They're all silvery metals. They have very similar chemical properties. They basically have 2, 3, and 4 valence states. So the chemistry of all the rare earths are pretty close to each other. But they have very, very interesting magnetic and most, for our purposes, optical properties. And that's because of all of the energy levels that exist in the F electrons for these atoms. So these shells, basically these F shells, transitions take place in those electron transitions take place between energy levels, which give rise to wavelengths that are of particular importance and very useful to many industries like the laser industry and for amplification and telecommunications. So it's very, very interesting materials to provide optical gain for lasers. And they can be used to fabricate solid state lasers. Many lasers right now, like the ND YAG and neodymium YAG. The neodymium is a rare earth. That's the actual atom that's lasing in that particular medium. So in order to understand what this is all about, let's give a quick review of how a laser works, a very simple overview. Basically 3 components that make up a laser. Basically, it's made up of an optical cavity, which is basically 2 mirrors here, where a photon can bounce back and forth. Simple as that. And then inside the cavity, there's, excuse me, there's a gain medium, and this is where the rare earth would be contained. And this gain medium would be able to provide the lasing media. And then also we're going to need an energy input, something to provide energy into the system. So the way the system works quickly over here is I show a 2-level system basically. So you have an energy level, a ground state, and a higher level. And there's a certain difference in energy between these 2 levels. And if a photon comes in and exactly matches that energy level, it will absorb that photon and cause the electron to jump from E1 to E2. So that's called absorption, and that's something that happens all the time. That's the way the world works, so to speak. But the interesting thing is, if you have an atom that is in the excited state, and a photon comes along at that energy difference, it can actually cause that electron to drop from the high level to the low level, emitting a photon, and that photon will be in phase with the incoming photon and at the same wavelength. And this is what allows you to build up photons on top of photons to make a laser work. This is called stimulated emission, and hence the laser acronym, light amplification by stimulated emission of radiation. So that's basically how a laser works. And then, so I'm going to jump over to one other thing I want to say back at this slide is that an amplifier is basically the same setup except without the mirrors. There's no cavity. It's just basically a gain medium. So we go over to what are we going to use these things for? So for optical fiber telecommunications, we're all very much aware of this industry, very, very low loss fibers. We guide around bends, high data rates, immune to EMI, electromagnetic radiation, and it's cheap to produce and very robust. Our whole telecommunications system is based on it right now. I'm just showing a basic loss curve here, and you can see that at the operating wavelengths of, say, 1550, we get very, very low losses on the order of 0.3 dB a kilometer. However, before the advent of rare earth dope fibers, about every 100 kilometers, if you think about it at 0.3 dB a kilometer, 100 kilometers is a 30 dB loss. Now that's quite a bit of loss. You're losing most of the energy. So you see input signals coming in, and at the end of 100 kilometers, the signal is being lost. This requires that you have to have these regeneration stations, these repeater stations, where signals have to be detected. They have to be from the optical domain. They have to be converted back into the electrical domain. They have to be remodulated, launched into the fiber again. And this repeater station has to happen every 100 kilometers. And it's kind of a big deal to have to do that. But so now along comes a rare earth dope fiber. What if we could put a rare earth into the core of an optical fiber, which was developed? So we can do that now. So if we put erbium into the fiber core, the fiber core now becomes an amplifying medium. And in this very small diagram down below, it's a very simple sketch of how an erbium amplifier works. But this fiber, shown here in yellow, is basically doped with erbium atoms. The signal itself comes in at, like, say, 1.54 microns, and it's got a certain level. It's low, okay? And I put in a pump laser. The pump laser is at another wavelength, which can excite the atoms, the erbium atoms, and get them kicked up to high energy levels. And then when the signal comes through, it gets amplified, and the output signal is greatly increased. So you don't have to go back to electronics. You can stay in the optical domain. This is a relatively simple device. I mean, in reality, there's lots of complications, but it's simple in concept, and it can provide a huge gain for the signals on the order of 25, 30 dB of gain. So it actually is what enabled what we have today for the bandwidth that we enjoy with tremendous communication capability. So this was a big breakthrough for telecommunications. On the other hand, another use for the rare earth dope fibers is to make a laser. Like we said in the original slide for how a laser works, we can basically make a laser by, here I show a ytterbium dope fiber. It's in the core of the fiber, so that's the gain medium. These things on either end are fiber Bragg gratings, which are just essentially mirrors. So you can set the mirrors to be what you want them to be. And if you pump it with the right wavelength, it will absorb a photon and excite the atoms in this core. Then it will begin to laze, and you'll get a fiber laser output. So this was a big breakthrough, but in the early days, the fibers were only core pumped. Basically, you had to have a pump diode that would couple into the core only. The power was limited at those stages by the available pump power of the laser diode and the fact that it was very difficult to couple that laser power into the optical core. Major issue basically here is it's great to have the fiber laser. You know, in the early days, they were putting out milliwatts, hundreds of milliwatts, maybe up to a watt, but high power wasn't in the cards. And the major issue is, how do you scale that up? You have to be able to get more pump power in there. So back in the days when I was at the Polaroid Group, we had the idea about coming up with a double clad fiber design, which essentially puts a core, the ytterbium dope core, it's like a fiber in a fiber. There's another cladding around the core, which is much, much larger, and also has a low index refraction material around it. So you can come in with very low brightness, high power pumps and you can gang them up, many laser diodes, and couple them into this big core, on the order of 300-400 microns in diameter, even higher. And that will be absorbed by the rare earth or ytterbium doped core in the middle. It will gain energy, get excited, and then it will begin to laze. Now, this was able to produce very high powers. Many things have been done where the power levels go up into the kilowatt range. So it's very high power, diffraction limited output. They use it for cutting and welding and material processing, medical, and it's turned into actually a multi-billion-dollar industry right now. All the laser welding and cutting is done with fiber lasers now. So capable of super high powers, tens of kilowatts. The real advantage is the overlap of the energy coming in from the pump with the signal. Because it's a fiber in a fiber, it's very high. So you get very high efficiency out of this. The output beam quality is guaranteed by the fiber. So you get, single mode operation if that's what you're going after. It has a very high surface to volume ratio, which is great for heat extraction. One of the big problems in the regular, like YAG doped, neodymium YAG lasers that are flash lamp pumped, is that they use very short rods that are big in diameter, and it's hard to get the extra heat out. So with a fiber laser, it's very easy to get the extra heat out. So it helps very much. It's very high power and very high conversion efficiency, which leads to wall plug efficiencies that are quite high, on the order of 30 to 35% overall wall plug efficiency, which is quite good. This is actually an older graph showing some of the accomplishments that have been done in fiber lasers over the years, with Southampton at 1.2 kilowatts and IPG up at 10 kilowatts and even 40 kilowatts. So these are huge powers that can cut through, multi-centimeters of thick steel and other metals very quickly. So, okay, so those are basically the main applications: fiber lasers and fiber amplifiers for rare earth doped fibers. There are other applications, but they're usually in sensors and things like that. So it's much less in the manufacturing area right now. So how do you make these fibers? So before we can get into that, we have to look at some of the process for how do you make a fiber, basically. So there are many types of processes that are used to make optical fibers. One of them is called modified chemical vapor deposition. It's MCVD, and it is a process that is widely used. It's very flexible, so a lot of specialty houses use MCVD, but it's not the only one. But I'll be talking specifically about MCVD in this case. So modified chemical vapor deposition, just a quick overview of how it works. It basically starts with a silica tube that's put on a glass working lathe. Basically, the tube is hooked up at the input end to be able to provide gases and dopants that are vaporized. And on the output end for exhaust, there is a hydrogen burner that is on a carriage that traverses the length of the tube. And what happens is you basically bubble oxygen through, in this case, I show silicon tetrachloride, which is the primary glass former. And that reacts with oxygen in the hot zone here, and causes the reaction causes the silica to become SiO2, which is basically glass silica. It comes out in the form of a soot. It's basically a white, tiny particles. They also travel downstream and they deposit on the inside of the tube. And then as the burner traverses down to the right, it basically consolidates that silica, that soot layer, into a uniform glass layer. So that's a basic overview of MCVD. The precursor chemicals, basically halides, silica, you can dope with germanium tetrachloride, boron tribromide, however, there's phosphorus oxychloride, things like that. You have a traversing burner and multiple passes now. So one pass deposits a certain amount of glass, maybe on the order of maybe a 0.5 millimeter square to up to 1 millimeter square per pass. And then you can put down multiple passes, and you can control the dopant concentrations as you put down the passes. So you can control index profiles. And so it has a lot of flexibility and ability to do that. Once you've done all that, then the tube is heated up and it's slowly collapsed, and then finally collapsed down to a solid rod, and that becomes the preform. The preform itself is then what is drawn into a fiber. So that's an overview of that. So, and here's what the vapor deposition system looks like. Silicon tet I show here, germanium tetrachloride, boron tribromide, and phosphorus oxychloride. There's lots of other chemicals that can be used, but those are the standard ones that were used in the industry. So how do we add the rare earth? It's basically 3 different processes that are used right now in order to be able to get the rare earth. One of the issues with the rare earths is that if you look at them and compare them to the chemicals that are used to make the MCVD process work, the silicon tetrachloride and the germanium tetrachloride have relatively high vapor pressures. I can bubble through those, and I can vaporize the material, and I can bring it into the hot zone. So the rare earth halides basically have pretty high vapor pressure. So that's difficult to transport the material. So how do we get the rare earths into the hot zone? So there are 3 basic methods that have been used. One is called solution doping, and then there are 2 vapor phase methods. One of them that use what they call a chelate precursor, and I'll go over that, and the other is the halide precursor. Now the halides were looked at originally. I don't think people liked them because they had very high vapor pressures, but there was some other issues going on there. So I'll get into that a little bit later. So each of these things have their advantages and things. So in the solution doping process, basically when I talked about putting the soot layer down, the burner would traverse down the tube and then consolidate that. But in this process, they took basically the flame and turned it down so the temperature wasn't as hot. So you would put down a soot layer, and there would be some partial consolidation, but you wouldn't consolidate it completely. The glass particles would sort of stick together on the inside of the tube, but there would be space in between the tubes. So then the solution doping process, basically the tube is taken off the lathe, and then it's filled up with a solution of a rare earth chloride. And that rare earth chloride will then permeate the soot into the interstices between the little silica particles that are sort of stuck together. Then you let it come to equilibrium, and then solution is drained out, and then you have left this soot that's permeated, leaving with the rare earth behind after you drain it and you dry it. And now you've got rare earth chloride that is sort of sitting in the interstices of the material. Then the soot layer can then be sintered, and when you do that at high temperature, you're converting that rare earth into an oxide. Basically, it mixes with the silica glass, forming a doped silica layer. Now, this process can be repeated many, many times in order to build up the core area. So the tube can be processed the same way into the solid rod. The main advantage here is that it's easy to use and very, very simple. It doesn't take a lot of capital equipment to be able to do it. The disadvantage, though, is that you only can do 1 layer at a time, and you're taking the tube off the lathe every time you put down just 1 layer. So if you wanted to do like 10 or 15 layers, which is pretty common. Actually, MCVD does many, many, many layers, much more than that, and for some preforms. It can get pretty daunting to take the tube on and off the lathe continuously. It could take 15, 20 steps and take actually weeks to produce a large core preform with rare earth. On the vapor phase area, basically, there's 2 common ways to do it. One is to use what they call a chelate. And a chelate is an organic metallic compound designed to give the rare earth some vapor pressure. So the common one here, I say 2266 tetramethyl 3,5-heptane-dione, a big name for a lot of organic molecule, basically, that basically there's 3 molecules of this stuff called THD, and 3 of those molecules act like a claw. That's where the word chelate comes from, and basically picks up the rare earth atom, and now you can vaporize it at relatively low temperatures, somewhere in the 200-degree range, 200 centigrade range. And so you can actually vaporize it and then bring it in like you do the other chemicals. Now, these also have their advantages and disadvantages. So the advantage is it's relatively low temperature, even though the temperatures are much higher than what's used for silicon tetrachloride and all, it's still relatively low, around a couple hundred degrees centigrade. They're easy to use, they're non-corrosive, and they're non-hygroscopic, so they're easy to handle. The disadvantage, in my opinion, is that, because it's an organic material, basically there's a lot of hydrogen in it. It's basically a hydrocarbon to keep the chelate. And there's, like I say here, 57 atoms of hydrogen for every atom of rare earth that gets into the hot zone. Now, water is a big problem for rare earths, so we want to keep the water as low as possible because it's an absorbing ion, so we don't want that. So it's and people have been able to use different kinds of drying techniques to make this and the solution doping process a little bit better for water incorporation, but in the MCVD overall way of thinking of it, you want to really keep the hydrogen out if you can. So I don't like the fact that there's so much hydrogen going into the hot zone. Vaporization control is very difficult as well because you can't get it too hot, because if it gets too hot, you'll break it down. The organic material will break down into a black tar. And if it's too cold, obviously it will condense. So you have to keep very, very tight control of all of the lines that bring the chelate material to the MCVD system. High concentrations are hard to control as well, because if you can imagine, you have oxygen in the tube because we have to make the silicon dioxide. And if I have a lot of hydrocarbon in the tube, at the same time, there's a lot of rare earth chelate in there, the actual chelate ends up burning. So you end up with a blue flame that travels down the tube, and that sort of wrecks all of the deposition. And it's a little bit hard to do very, very high concentrations. It's also the chelate organic materials are not very compatible with the standard halides. Halides are very strong oxidizers. So when you mix the chelate materials with the halide materials, they can break down even prior to getting to the hot zone. So that's a big issue. That's a problem. And the other issue is, with the chelates, you have questionable purity levels because you don't know, who's making it, and there could be other ways to get contaminants into your system that you don't want. So now we turn over to the vapor phase using halides. Now the halides, it uses rare earth chlorides, and the rare earth chlorides are very, very high hygroscopic. So if you leave them out in the air, they'll just latch on waters of hydration, and they will have very, very low vapor pressure. Now, anhydrous, if you can get rid of the water, the rare earth chlorides have a reasonable vapor pressure, and at high temperature, quite high, on the order of 800 to 900 degrees C, you can vaporize enough material and produce enough to get very high concentrations and be able to control those concentrations. So a properly designed halide system, if you address the engineering issues, it allows you to take advantage of the fact that you can have a high vapor pressure and have an anhydrous material without any water. As a matter of fact, you have to have that or it really doesn't work well. And it's very difficult to get anhydrous materials from vendors because it's so hygroscopic, it almost always will gain some water. So, so that's basically the overall process. So I would welcome any questions that anybody has. I think I did okay on the time, 35 minutes or 30 minutes. So
Yeah.
I'm all set here. Yeah.
Yeah, Rick, just fabulous, and this is really where the photons hit the road, right? It's
Yeah.
really, really good technologies and very practical in how we're trying to move photons. And what with the evolutions of quantum computing and all that, we got to move those little photons even better and more efficiently. So, very good technologies. If you have any questions, those of you in the audience for Rick, please take this opportunity to enter them in the chat function. A couple questions I have. Could you elaborate a little bit more on the advantages and disadvantages of the chelates versus the halide doping systems? I was just trying to understand the differences.
Sure. Yeah. Yeah. As I was saying before, the with the chelate system, I mean, the thing that's nice about it is that it's a relatively low temperature process. So you don't have to deal with the very, very high temperatures. And you can actually provide sufficient vapor pressure in order to get rare earth atoms into the hot zone. So it works well that way, but it's extremely hard to control because you need to really control a very tight temperature range for the gases that carry the chelate material to the hot zone. It can't be too hot and it can't be too cold. So it requires a lot of detailed design of the delivery system. And in addition to that, there's the problem with not being able to get high concentrations very well. And because of the fact that you end up with a flame inside the tube, which is very disadvantaged, that actually causes pressure disturbances, screws up the soot deposition. It really makes kind of a mess inside the tube. So that's not very advantageous. And then the other thing is about the purity. That's probably less of a concern. It depends on the rare earth system that you're using. But those are kind of the disadvantages of the chelates. The halides are nice because if you have an anhydrous halide, it can be very, very pure. You can obtain, meaning buy, rare earth oxides and chlorides at very, very high purity levels, 5, 6 nines in some cases, which is a good thing to have. It's especially a problem for ytterbium. We could go back to the periodic table there. If you notice, the thulium and ytterbium are right next to each other. Thulium is a contaminant for ytterbium. You don't want thulium in the ytterbium. And thulium is so hard to separate from the ytterbium because it's right next door to it. It's got extremely similar chemical properties, so it's very, very difficult to get those thulium atoms out of there. But they have achieved that with making the halides. So once you get the halides, now you have to process them yourself. But we have a system that we sell basically at Fiber Optic Center to do the halide process, and we have a process to convert hydrated chlorides to anhydrous chlorides, and that's the key to the process. And with that, now I can just make a preform in I can do a 2.5 to 3 millimeter core in 8 to 10 passes. I can make a whole rare earth dope preform in 1 day, and we used to literally do that. We used to make one a day without problem, and these are large cores. So, and I could get very high concentrations. We made 8.5 weight percent thulium concentrations with the. I could never achieve that with a chelate system. I don't know that I said this, but I basically was one of the first to actually use chelates back in the day, back in the 1980s, and since then have transferred over to the halide process. I prefer the halide process over the chelates. So I
Uh,
do have, actual experience with both processes.
Well, that's great. If someone were to purchase the halide system, what kind of processing support um, does your organization provide?
Yeah, Fiber Optic Center, actually, if you do purchase a system, we will provide the entire process. So we will provide everything that
Hmm.
you need to know, teach you how to make the anhydrous material, and then we provide the equipment and then teach how to do it. And actually will demonstrate, um, certain, coming to an agreement with the customer, whatever they want to see for a rare earth, sort of a, a ytterbium fiber or a thulium preform or whatever they want. And we will demonstrate that on site.
Right. And what type of information does Fiber Optic Center provide on adding, say, a low index acrylate coating as a secondary cladding?
Oh, well, yeah, that's an interesting question. Yeah, we can provide, because I have a lot of experience in that area, because
Right.
the cladding material that we use a low index coating to be the second cladding for the double clad fiber. So I have spent a lot of time with developers of low index coatings, and I have pretty good relationship with people that make these coatings, and they can be specifically designed for certain applications. So yeah, we can provide a lot of guidance in that area on where to
Right.
get them, and if you have a special requirement, you could actually even develop something new.
Yeah. For those who are already working with the rare earth chelates, like you said, that older technology, but are interested in the halides, what would your advice be as they transition, and how could you help them do that?
Um, yeah, well, we can definitely help with the transition over to a halide system.
Hmm.
The chelate systems, I had developed my own chelate system back in the 1980s. Subsequent to that, there have been a few companies that have provided chelate systems. I'm not actually privy to their exact design. I could provide some consulting help to people who have chelate
Hmm.
systems, if they'll let me know what the design is and how it works and stuff like that. We could probably work through some issues. But my recommendation would be if to go ahead and try to get yourself a halide system, and then I can show you how to make these things.
Yeah. Well, that'd be very helpful. Again, very interesting technology. What considerations are there to terminate and polish these types of fibers? Stripping, cleaving, polishing, for high-powered handling, epoxies, etc.
Yeah, there's a lot of actually that's a huge area all by itself. All the
Yeah.
packaging with fiber lasers is really a big deal. If you don't you should not sort of like underrate how much goes into that. It's very important. So yes, you do have to have good cleaves. You have to have good splices. They have to be low loss. And one of the biggest problems is what do you do with the extra pump that doesn't get absorbed? That has to be dumped. So they make certain
Mhm.
kinds of pump dumps and things like that. It's basically management of the photons in the fiber laser. That's what you have to do. You have to manage the pump, and you have to manage the signal. Um, but there have been some companies out there that have done some incredible work. Coherent done fantastic work. IPG, obviously, they're the leaders in the area. Really tremendous breakthroughs with incredible power levels. It's really quite astonishing. When you talk about 3, 4, 5 kilowatts in a single mode beam that's diffraction limited, that you can focus down to a couple of microns, that's that's going to blast through anything. That's a lot
Yeah,
of power in a small place.
absolutely. Is the halide process preferred for fibers for very high-powered lasers?
That I don't know. I know that we've used it for high power lasers, but
Mhm.
I'm not privy to all the processes that others may have. to make high power fiber lasers. So it's not clear to me on that. I know that we can do that. When I was at Coherent, we made 3 and 4 kilowatt lasers um, without an issue. So, but so have some of the competitors like IPG. IPG makes their rare earth dope fibers somehow, which we don't know how. They keep
Right.
that to the chest.
Good.
Yeah.
Um, can the same processes be applied to soft glass preforms like rare earth doped ZB land fibers?
Yeah, actually, that's a very interesting question. Yes, for the
Yeah.
Z-band fibers, certain rare earths will have transitions that only happen in the Z-band fibers. So, having to do with the phonon energy of the material, which is the lattice structure of the material itself. Silica is not always the best material to put the rare earth in. The Z-blands work really, really well. They have their issues as well, but yes, they make Z-band fiber lasers. It's very interesting work. And then you mentioned that the earliest work, the actually the fiber laser was first demonstrated by Elias Schnitzer, the guy that I worked for at Polaroid, and it was a soft glass fiber. It was a neodymium doped rod in tube fiber that was made with a rod in a tube, soft glass, and he flash lamp pumped it and got it to laze. So that was done back in 1961, I believe. That's going back quite a ways.
Right.
Yeah,
Um,
so this is good.
Good. And for those of you, for those folks that already have current equipment that they use, but would like obviously any kind of transitioning to other types of equipment, how could your organization, yourself, or Fiber Optic Center help in evaluating or have any folks that have any questions with that equipment? And do you know of other equipment that might be unique and additive to their process?
Um, well, we could provide, well, we could provide a system, a halide system, but I think we would insist that it go on SG controlled equipment.
Okay.
Um, that SG is the ones that makes this particular halide system. So
Okay.
it's compatible with their system. Could it be made with another system? Yes, but that's a lot of work. It requires all sorts of redesign and stuff like that. And I don't think SG would be interested in doing that because it's just it's not economically feasible for them because
Very good. Yeah.
they are the system designed. Yeah.
Okay. Um, for those of you in the oh, I have one more question here that popped up. What are the main parameters that need to be characterized post-production to ensure performance?
You mean so laser characteristics and things like that of the fibers? Is that the same?
Y- Yeah, I think, that basically what's your goal characterizations, and then
Okay.
obviously that optimizes the performance of the process.
Correct. Yeah. Actually, yeah. So that would be, we would measure the fiber for loss in the areas where the rare earth doesn't absorb, obviously.
Mhm.
And we would look for low water loss, at least typically routinely less than 15 dB a kilometer at 1380, which is like a quarter to a third of a ppm of water. It should be that or less. And then you want to look at the absorption, the concentration of the rare earth, the absorption spectrum of it. You want to know what the absorption. If you have a double clad design, you want to take an absorption scan of the double clad fiber so that you know how much fiber you'll need to get, say, 13 dB of absorption when you're making a fiber laser. And it would be a good thing, I think, to have a setup where you could measure the quantum efficiency of the laser. And that's not that easy to do because there's a lot of things that get in the way of it. Things like, the mirrors and the cleaves and all that stuff. But there are setups that you can use that sort of eliminate all that. that you could just get a nice quantum efficiency number. You should be somewhere in the 73 to 76% range for efficiency. That's overall efficiency. That's not quantum efficiency. That's overall efficiency for your turbine. For your turbine, I have to qualify these things.
Good. You can see on the screen some links to ask further questions of both Rick and Fiber Optic Center. So you can see an email there. I will also now provide you with Rick's direct email contact so you can reach out to him. But again, Rick, I want to thank you so much for the time and the great experience and work that you have accomplished throughout your career and now continuing to bring this knowledge and information to our industry. So again, great presentation. And again, for those of you in the audience, you can see Rick's email address here at the top if you want to reach out to him directly for any more questions. And also, I want to remind you that these webinars from IWCS are presented typically once or twice a month. Our next technical paper webinar will take place and typically takes place on the third Friday of each month, but the next one will be on Friday, August 15th. And you'll be receiving an announcement for these events, so please feel free to share that with your colleagues so that they can also join and register as well. And before we conclude, I must recognize and express our sincere appreciation for our IWCS partner level sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global communities. So again, thank you to these leading suppliers in our industry for their support. As I mentioned earlier, we are very excited at IWCS. Today, actually, we have launched our registration for our summer specials for those of you who want to get a good deal and come to Pittsburgh, Pennsylvania, here in the USA. Fiber Optic Center will be there in the exhibition, and I'm sure you'll be able to catch up on this topic and many others. But we are excited to be in Pittsburgh. It's a new location for us, but it's a great place to visit. The city has really revitalized itself. So we hope that you'll take the time to come and network with your colleagues from all around the world and see some incredible presentations. This will be our 74th annual Cable and Connectivity Industry Forum. So it'll take place at the end of October, on October 27th through the 30th. And this year, we launched this concept a few years ago, but this year we're in the process of developing 4 fantastic special sessions that might also be of interest to you. In addition to our normal technical papers, we're going to have some really leading, trending topics such as AI and machine learning specifically for communication network infrastructure, sustainability, of course, an ongoing important topic that our industry can contribute to and is already doing, particularly in the fiber optic world, and a great new initiative called SOFIA, which is trying to bring sustainable information together as a collective industry to our customers and to the world. Also, a topic under consideration is EV-powered cables for electric vehicle applications, and then also the important world of smart grids, obviously the convergence of power and data. How do we power the grid for the future and have real smart connectivity resilience, and innovation to bring all this together into a more efficient world. So, some great opportunities. We really hope you'll join us and check your inbox to see the early bird registration specials as we build up towards the conference in October. So again, thank you for participating today. I did see a lot of you are late into the night, but we hope you have an enjoyable rest of your day and evening and a great weekend ahead and a fantastic summer as we rapidly get through the summer with your family and friends. So thanks for being with us and hope to see you again next month.